Good morning, students. In the last class, what we have seen is composite cylinder problem we have seen, and we have also seen the concept of critical radius of insulation, and we have solved the problems based on that. Today, we are going to look at the composite sphere case. Okay, for this composite sphere case, here I have written 3D heat conduction equation in spherical coordinate system. 3D equation in spherical coordinate system. I have written it here. Okay. So
I'll consider a sphere here, okay, and the sphere will be having so and so radius. Let me consider a hollow sphere here. This is a hollow sphere with so and so radius. Radius and all I'll take later, but I'll consider certain assumptions here. The assumptions go like this. What I'll do is I'll consider it is one dimensional, that is r comma theta comma phi is the spherical coordinate system. For that, theta and phi will get cancelled, only r will be there. That is one dimensional thing I am considering. And then I will say that the qgen is 0, that there is no internal heat generation. Also I'll consider that it is a steady state problem. When it is a steady state problem, with time the given property will not change. That is, what it will imply is dt by dt is equal to 0. That's what the meaning of this. So, given that these are the assumptions that I have, okay, along with these assumptions, I can also write that it is isotropic and homogeneous. When I say it is isotropic or homogeneous, that means that the kr is equal to k theta is equal to k, meaning the value of thermal conductivity is not varying with respect to the space coordinates. Okay, that's what the point is. So if theta and phi can be neglected, this term can be neglected. Okay, this can be made zero. This is a phi term. This can also be made 0. Theta term is made 0 and phi term is made 0. Qgen is also taken as 0. This can also be made as 0. This is also a 0. This is also a 0 because it is steady state dt by dt is equal to 0. So your governing equation will be 1 by r square into dou by dou r of r square into dou t by dou r is equal to 0 will be the governing equation in this spherical thing. Governing equation. So this governing equation is representing your case, the spherical coordinate case here. That is, everything is gone here except the first term. That first term is equating to 0. That is your governing equation here for you. Right. So, given that this is a governing equation, what to do next? You have to integrate it appropriately. If you take this 1 by r square, no, this 1 by r square will go into 0. That need not be taken. Okay. So, the equation will be like dou by dou r of r square into dou t by dou r is equal to 0. That is your equation. And now I'll integrate. When I integrate, what happens is r square into dou t by dou r is equal to c1 will be the expression. Because if you integrate, if you differentiate this expression, you will get this expression. So if you integrate, the reverse will happen. So this is the thing, and I'll integrate it again by taking the variable with separable. So what I'll take is dou t is equal to C1 by R square into dou R. I'll take. Now if I integrate it, what happens is t is equal to C1 by 1 by R you will get, because the integral 1 by R square is minus 1 by R plus C2. So this will be your general solution. General solution. And now that you got your general solution, you have to apply the appropriate boundary conditions. When you apply the boundary conditions, this arbitrary constants C1 and C2 will be removed from this equation. How to remove these? For this, you have to apply the boundary conditions. So, yet R is equal to R1. Let me say the temperature is equal to T1. And yet R is equal to R2. T is equal to T2. This is the Dirichlet boundary condition, that is the temperature boundary condition. I am applying at the boundaries, that is radius 1 and radius 2. Let me call this equation as 1, this one as 2, this one as 3. If I have to represent these two the boundary conditions in my diagram, it goes like this. There is a hollow sphere here. This is R1, this is R2. The temperature that is prevailing here is T1. The temperature prevailing on this end is T2. It's a sphere. So that's how we can represent these boundary conditions on the diagram. Fine. So now what I'll do is I'll substitute 2 in 1. We'll substitute 2 in 1. What I get is T1 is equal to minus C1 of 1 by R1 plus C2, and I'll substitute 3 in 1. Then I'll get T2 is equal to minus C1 of 1 by R2 plus C2 I'll get. Let me call this equation as number 4, this equation as number 5. Now what I'll do is I'll take the difference of 4, equation 4 with 1. That will give you T1 minus T is equal to minus C1 you will take common, and what remains here is 1 by R1 minus 1 by R2. The effect of C2 will get 0, because plus C and minus C will be 0. Then I'll take 5 minus 1. When I take 5 minus 1, it is T2 minus, let me take 1 minus 5. What I want is T1 minus T2. For that I have to take 4 minus T1 is in 4, T2 is in 5. 4 minus 5 I will take. So it is T1 minus T2 is equal to minus C1 of 1 by R1 minus 1 by R2. Sorry, this is not R2, this is R. It is representing T. Now, let me give sorry, let me call this equation as number 6, this equation as number 7. Now, I will divide the equation 6 with equation 7. When I do that, what I get is T1 minus T by T1 minus T2. If I do that here, the effect of C1 minus C1 will get cancelled. And what remains here is 1 by R1 minus 1 by R by 1 by R1 minus 1 by R2. So that's how your equation will be. And this equation, you can take it as temperature variation equation. Temperature variation equation. That is a temperature variation equation. From this, can you tell what kind of variation is there here? The kind of variation that is happening in sphere. Can somebody tell? It is straight line in your slab case, and it is logarithmic in your cylinder case. Here, in this case, it is hyperbolic. In case of sphere, the temperature variation is hyperbolic. Okay, the temperature variation is hyperbolic. Either you can say it by looking at this equation, or you can also say it from this equation also. Okay, you can see that this is something like the T is one variant and R is one variant. So that is xy is equal to C kind of variation, which is a rectangular hyperbola. Okay, so it is a hyperbolic variation. Hyperbolic variation of the temperature you will get in a sphere. That is the thing. Now, what I want is I want the dou T by dou R value here from this particular expression. Okay, so from this, what I will do is first I will write T. So T is equal to T1 minus minus 1 by R by R minus 1 by R. That's how your equation will be. Now, what I'll do, I'll differentiate this equation T with respect to R. So what I get here is dou by dou R of T1 minus T1 minus T2 1 by R1 minus 1 by R by 1 by R minus 1 by R. Same expression I have written here. See, if I take the derivative with respect to T1, it's a constant value, so that will be a 0. So dou T1 by dou R, if I take, this will be right. Next thing is, I'll move on to this side. Here, T1 minus T2 into 1 by R1, this expression, whole expression is a constant expression. So I'll keep that expression outside of my derivative. And then if I take even with respect to 1 by R1, that is dou by dou R of 1 by R1, if I take, then this expression will tend to 0. Next expression what I have is dou by dou R of 1 by R I have. Okay, this is how your expression is, right? So this is 0. So this will be multiplied with this. This minus into minus will be plus. So what I get here is T1 minus T2 by 1 by R1 minus 1 by R2 into dou by dou R of 1 by R. It is minus 1 by R square. Dou by dou R of 1 by R is minus 1 by R square. So what I got is dou T by dou R is equal to, this is the expression that I got. According to my Fourier's law of heat conduction, Q is equal to minus Ka into dou T by dou R. This is my Fourier's law of heat conduction. Now I have dou T by dou R expression, and I substitute dou T by dou R into this. Let me call this as 8 and this as 9. Substituting 8 in 9, what you get is Q is equal to minus into minus will be plus, and I'll be writing that minus here. K, I'll leave it as it is. What is area here? Area is 4 pi r square. Because it is a sphere, the area, the surface area, the area with which the fluid is interacting, or area perpendicular to the direction of heat transfer, both are same here, and it is 4 pi r square here into the dou t by dou r expression which you got just now is t1 minus t2 by 1 by r1 minus 1 by r2 to 1 by r square. This minus is there here, minus is there here. If you multiply this minus minus plus, anyways, this r square is gone. So what you get here is q is equal to 4 pi k into t1 minus t2 by 1 by r1 1 by r2. This is your q expression. Okay, that is your q expression. Now, now that you got your q expression for a sphere, you can also get r expression for your sphere. R is nothing but the thermal resistance, that is delta T by Q. So if I have to convert this like a delta T by Q, what I get here is delta T is on the top here. So this will be equal to delta T by Q is equal to 1 by 4 pi K into 1 by yeah 1 by R1 minus 1 by R2. This is your expression. So it's better to write it that way. 1 by R1 minus 1 by 4 by K. This is the better way to write it. This 1 by this is how we'll get the expression for the thermal resistance. 1 by 4 by K. Right. So that is your thermal resistance expression. Okay. So similar to your cylinder case, again you have gone ahead here and you have got various values here. Okay. So it is like your cylinder case itself. There you got the same flow. Here also you got the same flow. Only the expression varied. It's the only difference. Right. Now let us move ahead and solve a problem. Here I have a problem. All these problems I am updating in your Google Doc. You may refer to. So let's take this problem and solve this problem here. Here, what is given as a spherical vessel is given in this question. It's a spherical vessel, and it has so and so dia. I have to draw a spherical vessel here. It's like this. First, that's in the dia. And then next is made of steel. So it has also got some outer thick outer radius because it has so and so thickness. You should also draw the outer thickness. So that is the outer part. And then what you have is it has so and so thermal conductivity. It has been insulated with two layers of insulation. So I have to represent two layers of insulation here. For representing that, I'm taking this here. This is one layer of insulation, and there is one more layer of insulation over it. If I take it, it goes. So this is what I have here. The thermal conductivities are given here. It is 0.05 here, and here it is 0.15. The thermal conductivity of this one, the inside one, is 40. Inside one is 40. So these are the thermal conductivities values given in watt per meter Kelvin. And what else is given in this question? The inside surface is at minus 196 degrees centigrade. Let me take this one. The inside surface, it is minus 196 degrees centigrade. Outside air, it is T outer is equal to 30 degrees centigrade, and H infinity is equal to 35 watt per meter square is given. He is giving you a contact resistance. R contact is equal to 10 to the power of minus 3 meter square degree centigrade per watt he is giving you. Okay, this is the value that is given to you here. So let us look into this. Okay, keep it aside as of now. See, what is given is this particular contact resistance is between the two insulations. That is, this is one insulation, the red color one, the green color one. And in between these two, R contact is considered. It should be clearly from the question. And determine the heat gain is asking. So Q value, what is the value is asking? Also determine the surface temperature and the overall heat transfer coefficient based on the outside surface area of the metallic vessel he is asking. So let us find out the T surface. T surfaces. What are these values he is asking? Okay, actually there are many temperatures inside that. Let's have all of them here. Let me take this resistance shape here. Now I have to draw the resistance circuit here. If I have to draw the resistance circuit here, how many resistances you will have here? Somebody please tell me.
Sir, 4, sir, I guess.
Four you will have a.
Maybe.
See, you will have four, correct? But
Okay, okay.
I will come to that.
So let me put 5 here. Why 5? I will tell you. There are 5 resistances here in this particular circuit. Why 5? Because the first one, the first resistance will be due to the resistance of the inside sphere. Okay, here in this case it is T. And next, adjacent to steel, what you have is this red color insulation, R insulation 1 you will have. And next, what you have is R insulation 2, which is in green color. Okay, let me write these things in. Same colors for clarity. This is R insulation 1. This is R insulation 2. Okay. In between these two, you have R contact. Many times this may be missed. Okay. This R contact is given. Okay. This R contact also should be considered. Okay. That's the thing people will miss. That's why you probably have said the four resistances will exist. But here there will be five resistances, and the fifth one being resistance due to convection that is present outside. Also, the temperatures are given here. This temperature, let me call it as T1, which is equal to minus 196 degrees centigrade. And on this side, I have temperature T infinity is equal to 30 degrees centigrade. Let me call this temperature as T2, this as T3, this one as T4, this one as T5. These are the temperature values. He's also asking you to find all these temperatures. T2, T3, T4, T5 is asking you to find. The overall heat transfer coefficient also, OHT, is asking you to find. This we will see in next class. For now, we will solve up to Q and T. Okay. How to get Q here? For getting Q, what you need is, it is the delta T by R total. Okay, if you can find out the individual resistances here properly, the sum of them will give you R total because all these resistances are in series. So if I have to get what is R steel, what is the formula? Somebody tell me. What is the formula? What is the formula for finding the resistance of the steel? Hmm? Just now we have found it out. It is 1 by 4 pi k into 1 by R1 minus 1 by R2. This is the formula. Okay. The R1 value is given in the question as 0.3 meter. So it is 0.3 by 2, that is 0.15. If I have to get R2 value here, it is 20 mm thick here. Since it is 20 mm thick, so I have to add the 20 mm to this one. So 0.15 plus 20 into 10 to the power of minus 3 will give you your R2. Somebody tell me what is this R2 value? After that,
0.17.
0.17.
Is it? Yes, sir.
Yeah, 0.17. Correct. 2 we will add here. Yeah. The next thing is R3. R3, if we have to take here, it is 60 mm thick again. Okay, each one is having 60 mm thickness. So this value will be equal to 0.17 plus 60 into 10 to the power of minus 3. So the R3 will be equal to 0.23. All of them are in meters actually. It is 23. And then R4 is equal to 0.23 plus 60 into 10 to the power of minus 3. That will give you R4 is equal to 0.29 meters. All of them are in meters. So these are all the radius values that you have. So appropriately you have to substitute it here. It is 1 by 4 pi k value is 40 in case of the first steel thing as given in the question, into 1 by R1 is 0.15, sorry, minus 0.17. So that will give you R steel. Next, R insulation 1 is equal to
1 by 4 pi k into 1 by R2 minus 1 by R1. That will give you, sorry, this is R3 here, 1 by 4 pi into 0. What is the first k value? It's given as 0 0.05. 0 0.05 into 1 by 0 0.17 into 1 by 0.23. It's not into, it's minus. Yeah. Next one is R insulation 2, which is equal to 1 by 4 pi k into 1 by R, sorry, minus 1 by R4, that is equal to 1 by 4 pi k is 0.15 now. And second case, it is 1 by 0.23 minus 1 by 0.29. This is R insulation 2. And then R convection, you have to get. R convection is 1 by Hk. It is 1 by H into area. Here if you take, it is 4 pi R R4, 4 pi R4 square. So that is equal to 1 by, the H value given in the question is, what is the value? It is
35.
35 into the 4 pi, and the R4 is 0.29 square. So some, calculate all these values and tell me. Yeah. What is the R steel value? What is the R insulation 1 value? What is R insulation 2 value? All these things. Along with this value is given as RS value. This RS value is given as 1 into 10 to the power of 5, 10 to the power of minus 5, right? Should be minus actually. Minus 3 here is given. So it is given in meter square Kelvin per watt is given. So this meter square should not be there here. To take away the meter square effect here, you have to multiply it with appropriate radius. Which radius will you take? Because it is existing between the insulations, the R3 will come into the play here. So you have to take the radius with respect to the R3. So the area is 4 pi R3 square. So that is equal to 4 pi into R3 value is 0.23 square. And if you take this, uh, multiply it with this one, so what you get is RS is equal to, if you want it in Kelvin per watt, if you want it in Kelvin per watt, what you have to do is 1 into 10 to the power of minus 3. The meter square is in the numerator. So this is meter square here. If you have it in denominator, it will get Kelvin per watt. The meter square in the numerator and denominator will get cancelled. So 4 pi into 0.23 square you will have in the denominator. So these two will get cancelled and you will get the value in Kelvin per watt. Tell me this value. What is this value? The value will be it is 1.5. What I have with me is 1.5. Cross check. And the power of minus 3 Kelvin per watt. So now I have all resistances in what do you call, Kelvin per watt. You can have minus 196. The delta T I am writing minus 196 minus 30. So minus into minus plus you will get. So by R total you will get. If you do that, you'll get the Q value. That's how we'll be doing Q on the temperature values. We'll solve in the next problem. Along with that, let's see the concept of overall heat transfer coefficient and solve it in the next class. So that's all for today. If you